Okay, dear learners, we have done our previous lecture, which is about the Gauss's law, the lecture number 12.7, which is also a topic of that book 12.7. Now we are going to discuss the next topic, which is 12.8. The topic name is the applications of Gauss's law. Applications of Gauss's law. Okay, before doing any application, before discuss any application, let's suppose how can there is a question: how can you find out the electric field intensity, and what is the systematic way to find out the electric field intensity? Actually, the main purpose of this law is to find out the electric field intensity of any charge configuration body. Actually, if you have any type of a body, any geometrical body which containing positive charge, which containing any charge, either be a positive or a negative, usually we suppose those bodies, and we suppose those geometrical enclosing surfaces having a unit positive charge, actually, not a negative charge. So for this sake, we define a surface which is called Gaussian surface. Gaussian surface. So what is this first? What is this surface? Actually, Gaussian surface is an imaginary surface which is usually represented by dotted lines, or we usually represent by a closed Gaussian surface. It might be a spherical, it might be a square form, or a box form, or rectangular form, but it should be a closed surface. It must have a unit positive charge. It must have a point through which we are going to find out the E, electric field intensity. Okay, so the Gaussian surface is an imaginary surface which containing a point, which enclosing a point through which we have intention to find out the electric field intensity. Okay, so how can you find out the electric field intensity? First, we will calculate all the total charge inside that Gaussian surface, and then we multiply by that charge by a ratio 1 over epsilon naught. Then you can be able to find out the total E. Like the previous lecture, we see that the Gauss's law is 1 over epsilon naught into Q times charge, the total charge. So when you be able to find out the Q, then you can also find out the electric flux or the electric field intensity. So now see the first application. The first application is the intensity of the field inside a hollow charge sphere. This is the first application of the Gauss's law. In this, in all the applications of the Gauss's law, we will define a surface, a closed surface which containing those points or the point through which we can find out the E. So first application is intensity, the intensity of field inside a hollow field, a hollow charged sphere. So from the statement you can estimate the idea. We have inquired that we will have to find out the E intensity or electric field intensity inside a hollow charged sphere. Suppose we have a charged sphere. Actually, the charged sphere mean to say that, of the charged sphere, let's suppose we have a sphere. Okay, now you can see that I have a sphere inside holding. So this is a sphere like a football. Actually this is a balloon. Okay, but suppose that this is a sphere. So inside there is no charge. This is a hollow sphere, but the surface is charged. Okay, but the surface is charged by a positive charge, but there is no charge in that surface. Okay, suppose we have another surface. We can represent this surface by a sphere Okay, this is a sphere which is positively charged but not inside, outside. Actually we charge the surface. Okay, there is a charge outside, not inside. Okay, so we have an intention to find out the E inside. Okay, there is no charge. Okay, so to find out the electric field intensity, I already explained that we need a surface which is called closed surface, which is called what? It's a Gaussian surface. Okay, so let's suppose the radius of that sphere is capital R, and for the sake of to find out the electric field intensity, we suppose a Gaussian surface inside this sphere. Suppose the dotted line closing surface is a spherical sphere surface and it has radius r dash, and the radius in that case r dash is less than r. Actually we inscribed a circle, inscribed a sphere, okay, not a circle, inscribed a sphere or a closed surface inside a hollow charged sphere, and we consider this is a Gaussian surface. Gaussian surface. Okay, this is a Gaussian surface, but keep it in mind there is no charge in that surface. So what will be the Gauss's law result? According to Gauss's law, which is equal to 1 over epsilon naught multiplied by q. Now you can see that there is no charge in that surface. What does it mean? Our q, it might be a plus capital or a small. Our q is 0. What does it mean? It means that if there is no charge inside the sphere, there is no field inside that sphere. So our result should be 0. Q multiplied by 1 over epsilon naught, where q is 0. When 0 is multiplied by 1 over epsilon naught, the result will be 0. So what does it mean? It means that actually, according to the electric flux formula, which is equal to epsilon naught dot surface area. Now you can see that actually surface area is not 0, but E is 0. Why E is 0? Because there is no electrical charge inside that body. Okay, so the interior of that sphere is a field free sphere. The hollow charge, if this is a metallic sphere, if you consider this is a metallic sphere and you develop a charge outer surface of the metallic sphere and the inner surface or the inside that metallic sphere, this region is a field free region. Field free region. So it means that as a consequences, as a result, we can say that any apparatus, anything which is placed inside that hollow metallic charged sphere is a free from the electric field intensity or a field. Or you can say that any body, any apparatus, any device which is placed in that metallic hollow charged sphere is shielded. Actually it's shielded from the electric fields. So most of the applications in daily application, most of the sensitive devices, sensitive apparatuses are enclosed by like that bodies. ज़्यादातर जो है आपके जितनी भी एप्लीकेशंस हैं, आपकी प्रैक्टिकल लाइफ की जितनी एप्लीकेशंस हैं, उनके अंदर जो है हम क्या करते हैं, हम मेटालिक स्फीयर लेते हैं और मेटालिक स्फीयर जो होता है एक्चुअली उसकी सरफेस जो होती है वो चार्ज होती है, बल्कि उसके अंदर जो है कोई चार्ज नहीं होता, होलो स्फीयर होता है, उसको हम इनक्लोज करते हैं ऐसी सरफेसेस के साथ ताकि उस पर कोई फील्ड जो है वो अफेक्ट ना कर पाए, उसकी परफॉर्मेंस को अफेक्ट ना कर पाए, उसकी जो पर्सनल फील्ड है उसको अफेक्ट ना कर पाए. सो दिस इज द practical applications of the Gauss's law. Now let's discuss the another practical applications or application of Gauss's law, which is nominated as by B. Now we are going to discuss next application of the Gauss's law, and we can see that how can we find out electric field intensity or electric flux through a charge sheet. Let's suppose this is the second application of the Gauss's law. The named second application is electric intensity. Electric intensity due to an infinite or infinite sheet of charge. So this is another practical, or this is another application of Gauss's law, actually, where we can find out the electric intensity due to infinite sheet of charge. Let's suppose we have a infinite charge sheet like this. If I'm going to discuss, like, suppose this is a sheet, okay. Actually, we cut off the finite portion of that sheet. This is a metallic sheet, suppose that, and we have charged this sheet. And this sheet is infinite, but here we have taken a small portion, a finite portion, and suppose that there are large number of charges. Okay, suppose that this shield is containing large number of positive charges. We have charged this shield by a positive charge, and this shield is infinite, and here we have asked to find out the electric field intensity or electric intensity. Now suppose that how can we find out the electric intensity through this charge shield. This is infinite charge shield, but we have taken off the small portion, finite portion. Okay, now for this sake, I'm going to draw finite portion of the sheet, and this sheet is charged. There are large number of charges in the shield. Now, as usual, we will define a closed surface. Like this, I'm going to find out the electric field intensity at that point. Suppose this is a point P, and we suppose a closed surface. Say this is a point P, and we have intention to find out the E at that point. Okay, student, you can see that if this is a charge sheet and there is a charge on both sides, or there is a electric field intensity on the both side, this side and this side. So there is also electric field on to the other side. Suppose this is by symmetrically, this is also a point P, and here is also electric field on the other side of that point, which is a charge enclosing a charge. Now we have suppose a Gaussian surface, which is closed cylindrical form surface, and here we have an intention to find out the electric field intensity at that point, which is P. Actually, this is that is the actual point, or that is the actual point with respect to this charge, and this shield is infinite, and we have taken a limited portion, which is finite portion. So by symmetrically we can see that if there is a electric field on the left side, and there must be a electric field on the right side of the charge sheet. Suppose like this, we have consider a cylindrical shape on the both sides, considering a point P which is symmetrically same this point and that point which is P on both sides, and we are going to find out the electric field intensity. So you can see that there is a field on that portion is EA, this is electric flux, and similarly there should be also the same result which is E dot A. Now the total electric flux on both sides should be E dot A plus E dot A. Okay, E is a electric field, A is a unit surface area. So the total electric flux should be 2 times E dot A. Okay, the total electric flux should be E dot A. Now according to the Gauss's law, we have seen that total electric flux is equal to 1 over epsilon naught multiplied by Q. Okay, so here we have a lot of number of Q's. The total Q actually described by the total electric charge density. Okay, so the sheet is infinite. We don't know how many charges are distributed on that sheet. Okay, so for this sake, how can we find out the total charges? By assuming the charge density, total charge density, and total charge density is, or charge density equals total charge, total electrical charge per unit area, So this is a total charge density, the number of charges or a total charge over per unit area, or you can say the number of charges per unit area. Okay, to represent this, it implies that the total charge density usually represented by a sigma sign, and total charge is Q, and the unit area is the A. Now by rearranging this equation, sigma equals Q over A, we can say that Q equals, it implies that Q equals A is dividing by Q, but by taking the A to the other side, A will be multiplied by sigma. Now you can see that Q equals sigma times A. Here we can substitute Q. Actually our intention is substitution Q, then 1 over epsilon naught, what is Q? Sigma times A. Now what is electric flux through this charge sheet? The electric flux is 2 times E dot A. Now replace this term by 2 E times A equals 1 over epsilon naught sigma into A. Now you can take this the only magnitude form. Okay, we can write in magnitude form. This is magnitude form. Now cancelling these two terms, A by A, it implies that when you cancel A by A, the only terms left are 2E equal 1 over epsilon naught times sigma. Okay, how our intention is that we have required to find E, electric field intensity or field intensity. E should be equal 1 over 2 times epsilon naught into sigma. Okay, so this is the electric field intensity due to an infinite charge sheet. Okay, if you want to write this expression in vector form, you can write this as in vector form 1 over 2 epsilon naught into sigma. And definitely we will have to write what? We will have to write a unit vector. We describe the direction of that E. electric field intensity. Okay, so this is the mathematical formation of electric field intensity due to an infinite sheet, which is equal to sigma time, actually this is not r, this is sigma charge density over 2 times of epsilon naught into unit vector r. So unit vector r actually normal to the, this unit vector is all normal to the direction of the E. This unit vector r is normal to the direction of E. So this is the expression for electric field intensity or electric intensity due to the charge, infinite charge sheet or infinite sheet of a charge. Now the third application of the Gauss's law is, we are going to discuss next subtopic, application of the Gauss's law. We have seen 2 applications. Number 1, intensity of field inside the hollow charge sphere. The other one we recently done is the electric intensity due to an infinite sheet of charge. Now we are going to discuss third application of Gauss's law, which is pointed as C, and the statement is electric intensity between two oppositely charged parallel plates. So this is the third application of the Gauss's law. Here we have to find out electric intensity between 2 oppositely charged parallel plates. Okay, suppose that we have 2 parallel plates. So how can we, there are 2 metallic parallel plates, how can we charge these 2 metallic plates oppositely? Simply we will apply electric field, or simply we will apply a high voltage. So positive, negative, this will carry a positive charge and this will carry negative charge. Okay, if these 2 plates are carrying 2 opposite charge, they develop electric field inside the plates to the edges of the plates, which is emerging from positive plate to the end of the negative plate. Here we have an intention to find out the E inside or between the 2 oppositely charged plates. So keep it in mind, the electric field inside a conductor is 0. Electric field is inside the conductor is 0 because when the you know that there are free charge carrier inside the conductor. These free charge carriers actually drift, and actually when they drift and one portion is accumulated by a positive charge, another is accumulated by a negative charge. Okay, and when you apply electric field, the distribution is disturbed and they cancel out the field inside the metal, inside the conductor. So inside the conductor there is no electric field, but the field is emerging is due to those charges which is at the point edges. These are those charges which are actually at the edges of the conductor. Actually those are which are the edges lines or the boundary lines of the conductor. So the field is emerging from those edges or from those boundary surfaces and moving towards the negative charge, which is actually penetrating, which is actually taking inside it. So same case is on the other side. Now we have intention to find out the E here between. So for this sake, actually space says that these 2 parallel plate, conductor plates, or charged metallic plates, oppositely charged metallic plates. There is a no medium between them. There is a free space. There is a vacuum. So the inner face of the one plate is originating the field toward the other inner face of the oppositely charged plate. So actually I have already told you that the surface charge density is uniform, and the surface charge density, we know that, is equal to the Q over A, or the total charge per unit area. Now if we consider a portion, limited portion, suppose if we take parallelly in horizontal direction, these are parallelly in vertical direction. Now the field originating from positive to negative, there is also a positive charge, actually not from here. So the pretty good thing is that we have inquired to find out the E inside those plates. Okay, for this sake, actually we say that this is all the charge is distributed on the edge surfaces of these metallic plates. So in that, these are metallic plates, these are conductors. So inside the conductor there is no field. Now supposing that Gaussian surface in a box form, we have considered, suppose this is a Gaussian surface, this is a box, we consider inside these between two metallic plates, which is totally charged, oppositely charged. Now say what, this is Q positive, now this is Q negative, and we will find out the electric field intensity between them. Now you can see that upper portion of this box is inside the conductor, inside the metal, inside the plate. So there will be no field inside the upper portion of the box, and also along the edges, the outer side edges, along this direction or this direction, there is also no field, because these are parallelly. These two edges, actually if we suppose that this is a box, and if I put the box here, you can see that the upper portion of the box is inside the metals. Upper portion is inside the metals. We suppose a Gaussian surface, we put the upper surface inside the metals of this box, Gaussian surface, closed surface, and the lower portion is below the plates, mean to say between the plates. Now you can see that the outer edges, this edge right or left, according to you, this is left and this is right. So these are parallelly. Okay, now you can see that the upper portion is inside the metallic plate, the lower portion is between the plates. Now also the outer side, the edges of this box, actually the boundaries of this box on the left or the right, according to you, because you are watching this video, you are watching this lecture, so according to you this is left and this is right. Okay, so according these two are parallel to the field lines, so there will be no electric field lines emerging on those sides, emerging into those sides. Okay, so कोई field जो है इसमें से नहीं गुजरेगी, but only this portion area containing the total field. Okay, so according to the last application, which is the due to infinite charge heat, and we suppose electric charge density. Here also we can suppose electric charge density and a large number of charges. Actually the field is producing due to those charges which is at outer edges, which is actually edges of the metallic plates. So the total Gaussian surface we considering here, the total electric flux through these Gaussian surface should be EA. Okay, but according to the Gauss's law, our electric flux is equal to 1 over epsilon time charge Q. It might be a smaller, you can also write the smaller Q or the in capital Q. You can also write the lower case or upper case. So here we can write this Q or capital or a smaller. So according to this, we can rearrange for this formula. Our Q or smaller Q should be equal to sigma times A. By using the surface charge density, we replace this by Q 1 over epsilon time sigma charge A. And also we know that electric flux through a closed surface is equal to E times A. So it implies that we can put the value E times A equals 1 over epsilon times sigma A. Cancel the A by A, you can have E equals, it implies that E equals 1 over epsilon times sigma. So this is epsilon, this is epsilon space permittivity or electrical constant. So this is the electric field, and in terms of the vector form, in vector form term you can write this as E equals sigma over epsilon into R. So this is a vector form. Okay, now you can see that how can we find out the electric field intensity in those three applications. And the vector, actually this unit vector is normally to the E in this direction from positive to negative, positive plate to negative, and this unit vector actually describing the electric field intensity direction. So students, those are the applications we have discussed, application A, B and C, and these all are actually the purpose of those, all the application is to find out the E, is to find out the electric flux, is to find out the electric flux density, whatever you want to say. So in applications of Gauss's law, our main or major purpose is to find out the electric field intensity or the field intensity.